Hello, we are Group 6 and here we present about Fourier's transform-based audio watermarking algorithms, published by Uski Sala, Khari Amin, Kafir Leduan, and Kalanes Fares. Digital media is integral in the modern age and it can easily be exposed to illegal manipulations. This paper focuses on protecting audio files using watermarking techniques, which are dedicated under the protections of copyright. The watermarks must have the properties of robustness, so the watermarks cannot be removed easily. Imperceptibility, so it doesn't visibly disturb the audio files, and capability indicates how much information can be inserted without being visible. Balancing between robustness and invisibility. A large capability has a positive effect on robustness, but a negative effect on imperceptibility, and vice versa.
Using three different types of Fourier transform for the experiment. First, discrete Fourier transform, which decompose a signal or image into some of elementary signals which are periodic and complex to allow amplitude and phase study of the system. The discrete Fourier transforms a psi of m times n as defined by this equation. Second, fractional Fourier transform. It allows to obtain a mixture of time and frequency components of a signal. A function of x with fractional order alpha is calculated as following equation. Third, quaternion discrete Fourier transform is generalization of two-dimensional complex discrete Fourier transform. It can be obtained by following formula. In the experiments, the process of integrating the watermark into order file is as follows. 1. Original order file is transformed into fast Fourier transform domain. 2. Real part of the high-frequency component is selected. 3. Coefficient parity is modulated according to the watermark bits. 4. Combine marked real parts with imaginary unmarked parts. 5. Inverse combination to generate watermarked audio file. The three types of Fourier transform are used with two variants. The first variant uses strict coefficients to conceal 2 bits of watermark. The second variant uses 2 coefficients to conceal 1 bit of watermark. As the signal energy is concentrated in low-frequency components, inserting mark in low-frequency component provides good robustness but introduces apparent distortion. On the other hand, inserting the high-frequency components make mark vulnerable to attack. Therefore, medium-frequency band is more suitable to integrate the watermark.
These are the results from the integration process. Figure 345 shows the discrete Fourier transform, the fractional Fourier transform, and quaternion discrete Fourier transform results, respectively. The red area represents the original audio file, the blue area represents the watermark file, and the yellow is the difference between the original and the watermark file. As shown, all of the transformations have little difference visually. To test the imperceptibility of the results, signal-to-noise ratio, mean square error, correlation coefficient, variance, and standard deviation were used. Focusing on signal-to-noise ratio in particular, where a high value is desirable and means that the level of distortion is low, the outcome are all as desired. For the robustness test, several attacks were executed on the watermark files, using normalized correlation to evaluate. A value of above 0.85 is desirable, which is true for all outcomes. Other related works are also used to compare the results. In conclusion, discrete Fourier transform and fractional Fourier transform offer good imperceptibility with the second variant, and the quaternion discrete Fourier transform is more suitable with the first variant. All the approaches are resistant to watermark deletion attacks while guaranteeing a reasonable signal-to-noise ratio. However, small audio files which offer less coefficient limit the capacity in the frequency domain, therefore less effectiveness. These are the group members, and thank you for watching.